I'd like to introduce Matt Evans, Computer Architecture and Security Advisor at Digital Catapult.
Thanks, Tyler. Good morning, everyone. Okay, I'm going to give you a short introduction to common vulnerabilities in modern computer systems. So it's 2022. We're surely experts now at building computers, writing software. We've been doing it for quite a while. Why do vulnerabilities still exist? Why do we still have them? Well, the short answer is computer software, computer hardware and software, both extremely complicated. And we are but mere humans writing it. Software is very difficult, and you shouldn't underestimate the power of a simple typo even, or a small error, to have quite catastrophic consequences in some aspects. We need to, as we're building these software projects, put a huge amount of effort into the security analysis. And I think it's fair to say that some projects don't necessarily put as much effort as others into trying to analyze all possible threats and trying to foresee all possible situations where something might go wrong. So as we try and build more and more complicated pieces of software, we try and deal with this complexity by scaling up our teams, by having multiple components, by having multiple teams dealing with those components. And when we've got multiple groups of people, we've always got scope for misunderstandings. And unfortunately, that's also a source of bugs, a source of issues that can lead to security problems. So perhaps design parameters or assumptions are broken when a module from one team is used in a different way. Perhaps just a global misunderstanding of what some of the threats might be or how your product might be used in practice. Reusing existing code that might be absolutely perfect might end up causing problems where that code is used out of its original design space, perhaps hitting some of its limitations that weren't really anticipated by its authors. And this has happened quite a lot, where a library, for example, might be used in a new context that wasn't anticipated, and with a new set of threats or information from malicious parties being parsed by an image library springs to mind. Code reuse is a good thing, though. I mean, we can't be writing everything from scratch each time. It's economically not viable, but also, code reuse gets a lot of eyes, particularly with open source code. A lot of eyes on the problem, and it makes code more robust. But we have to be aware of what the limitations are for modules or libraries that we import from elsewhere. But the final, I would say, the villain of the story, I would point towards C and C++ as languages I love, but have many pitfalls. I think we can all agree that they're some very powerful languages that let you do some quite funky things with pointers that are not always a good idea. And it takes a lot of discipline and a lot of care and a lot of effort to write really, really good C and really robust and secure C. So these languages are incredibly popular due to their age and various other, large projects using them. So we're not getting away from these languages anytime soon, but we're not really helping ourselves here. The choice of these tools exacerbates the challenges of complexity and trying to apply security or trying to make our systems secure. We use an enormous iceberg of software that comes from elsewhere. So we really are standing on the shoulders of giants when writing software these days. Most of that legacy software is C and C++. So looking a little bit more detail about what kinds of things go wrong. This is by no means an exhaustive list of the types of vulnerabilities or reasons they happen, but just to sort of give you a flavor. So for logic problems, perhaps a design choice doesn't age well or doesn't really anticipate some of the problems that may occur. So choice of weak cryptographic algorithms is one example. There are many, many ways for implementation of that design to provide scope for bugs, let's say. Not correctly sanitizing input from the outside world. Numerical problems are rife. That can be very fiddly to prevent overflow or signed and unsignedness issues, making sure all data is initialized correctly and so forth. These sorts of things are particularly problematic when implementing cryptographic algorithms. This needs special care, and this is a good example of why code reuse is a good thing. The rule of thumb tends to be don't implement your own cryptographic stuff. Use a tried and tested library that's really been hardened and had a lot of review and testing. Race conditions are quite an interesting example of where vulnerabilities can come in. So your design might correctly say, okay, well, we have some data from the outside world that's untrusted. Let's validate that data before we consume it. But if the implementation accidentally doesn't prevent that data from changing while we're checking it, then we have a problem. So, for example, an attacker can provide good data, get you to agree to it, and then change the data as it's being consumed, which leads to this time of check to time of use issue. I've saved the best for last. Memory safety issues are the majority of causes for vulnerabilities that are being exploited today. We'll see some statistics in a later presentation that are really very interesting. And these are particularly a problem with the languages C and C++, which is why I've called them out particularly. So doing an allocation, so in C you would malloc something, perhaps you do some interesting pointer arithmetic which causes an access off the beginning or off the end of that allocation. Perhaps you free something, yet it's accessed after it's freed. That will then lead to someone else perhaps being able to control your input data. When these sorts of issues occur on the stack, then we've got even more problems. So a buffer overflow on the stack turns an overflow or a data corruption problem into a control flow integrity exploit, potentially. And that can lead an attacker to have quite a wide range of interesting behaviors. And an attacker is able to do a lot of interesting things with control flow exploitation of our software. So there's some problems. What can we do about it? Well, unfortunately, we're not going to get away from good old-fashioned hard work, good engineering. And really, this is our development processes prioritizing security right from the start. So thinking in depth about anticipating problems, testing strategies, making sure that we're actively looking for problems and actively reviewing and keeping coding standards high to try and save us from ourselves in many ways, keep away from particular coding idioms which happen to be known to be problematic. Defense in depth is a really important one. So we have to do all of this hard work to prevent bugs, but anticipate that they will happen and try to layer our software or organize it in a way that will reduce the impact if bugs really are exploited. We heard a little bit before about areas where people are researching into improved verification and tooling. I think this is a major area. I'm very impressed by some of the kind of coding editor assistants these days, which can look at your code as you're writing it and suggest, well, do you really mean this instead, or is this idiom going to cause problems? But I think this is an area where we're going to see a lot of benefit to take a lot of the effort away from, or the complexity away from the humans, and have a lot more automation in the tooling that can help us avoid these bugs. Coming back to memory safety, well, I mentioned that C and C++ are kind of dangerous variables when we're thinking about memory safety. So one way of approaching this is to simply not use them and use memory safe languages, whether that's managed languages like C# or others like Rust, which will perform runtime bounds checking, and they'll prevent you from actually being able to make an out of bounds access. This is very powerful. The problem is we have that big iceberg of all of that legacy code as well. And in many cases, our software, we don't necessarily have the choice to not use C and C++. And wouldn't it be nice if we could bring memory safety to C and C++? Now, I've spoiled my own punchline here. So this is where Cherry is providing advances. So let's give a little overview of Cherry. The later presentations will give detail about how and why Cherry is doing what it does, but it provides two main features. The first, it provides a mechanism that enables us to write memory-safe C and C++ programs using these architectural capabilities that are introduced by Cherry instead of pointers. With some clever compiler technology, this can also benefit existing C and C++ code with a very low-touch improvements to existing programs, which is extremely important to help that big legacy of code that we're building our industry on. So this lets us this provides hardware bounds checking. So it lets the CPU do this bounds checking for us instead of the programmer having to think about it in the case of C and C++, or the runtime having to implement code to do this in the case of managed languages. So there are also opportunities in managed languages. So where you would have a runtime that might itself be written in C, then there are improvements to its robustness that Cherry can confer there. Or perhaps there are opportunities for the runtimes themselves to use capabilities and perhaps take some of that runtime bounds checking away and do that in hardware instead. The other really interesting feature that Cherry provides is there's that fine-grained compartmentalization. This gives us a low overhead isolation of software components, even in the same application process address space. So instead of existing methods where we might, for example, split an application across several processes and use shared memory, it's quite a coarse-grained memory management way of separating data out. This allows us to apply the principle of least privilege in a very fine-grained way to different parts of code running even in the same address space with a very low overhead. And this lets us think about software architecture in a different way. So separating out data that one particular part of the code shouldn't access. It's one of these, the purpose of these compartments is really to assign a footprint of data that the code in that compartment can access by design. And if an external actor finds some way of tricking that code into, using a random pointer from somewhere, it's prevented. So the code can only use the footprint that's that compartment is associated with. And this is a really powerful technique. I think that the scope for thinking about software a different way is going to be very interesting to investigate here. So I'll wrap up here and we'll hear more about how these benefits are realized in Cherry. Thank you.